Okay, let's get started. Any questions from the previous lecture or any? Good. So let's keep going with the K theory. So last time we discussed that, right? So if we want to consider massless spin one or massless vector field theory, so the Lagrangian takes that, right? So basically, we started building up first massive theory, and then we just set the mass parameter to 0 to get that, right? And then what we saw was that if we try to, in this language, so if I want to now study Lorentz transformation of this thing, right, for massless case, then I'm just rewriting what we discussed last time. We will find that, for instance, this vector field for massless case transform not just homogeneously like this, which you would be happy to see. Oh, yes. So for instance, this is transformation, and transformation is not like that. So if we found that vector field transform just that, we just have it, right? This is transforming as you expect. Everything's good. However, what we found instead was there is this space-time dependent and in principle this Lorentz symmetry factor dependent factor, which is like shift in a homogeneous shift. So that didn't look like last time. Obviously, we discussed in terms of polarization vector, like so. So we start out with the two independent polarization vector, and then we saw that under the Lorentz transformation, not only this guy will, for instance, transform with some prefactor, as you'd expect, but we saw that this guy also takes some momentum factor. So that's how I discussed, but I was rephrasing in terms of now this vector field. So what we said then last time was, okay, so in order to make sense of representation under the Lorentz group, what we have to say is that, so this shift is under the Lorentz transformation, transform, in addition to this factor, this these factors, we say that, in order to make sense of representation, we have to identify these two field configurations. Okay, so that was notion of gauge redundancy. Okay, so now we're going to continue, and then basically this was the discussion, and then we talked about the 2-degree freedom and so on and so forth. Okay, so now today we're going to talk about first coupling this theory to matter field. Okay, so that we talk about that. So we're going to talk about minimal coupling. Okay, so in order to get a sense of this, first let's start the following. So starting out with this matchless fault theory, and then let me just couple that theory to I don't know. So for instance, I have this vector field, and let's be totally agnostic. I don't know exactly what the microscopic physics, but suppose let's couple that to a source field. Okay. So now you can view this as a classical source field for now. Okay, this is classical source. So you can basically think of this as there's some sort of a vector field source, and then if you turn that on in some space-time region of support, you can view this as it's shooting out the photon. Okay, so in that sense, it is a source. Now, we will be now asking what kind of source we can actually construct out of the point. Yes?
We use the term minimal very frequently, right?
Yeah.
What do we mean by minimal?
Okay, good. So minimal, I mean, as I will discuss now, there is at the very least, structure that you have to include in order to be consistent with the Lorentz transformation and gauge invariance. On top of that, you can throw in extra stuff, which is also Lorentz invariant, gauge invariant, local, blah, blah, blah. But by minimal here, I mean, if you just, delete some of the terms that I will introduce soon, then that such a coupling simply is not consistent. So by minimal, I mean the set of terms I have to include in such a way that I can be consistent with the gauge invariance and Lorentz invariance and so on.
Okay, then can we prove that that minimality
Yes.
is the real minimality?
By real minimality, if you ask the question whether that is actually what's realized in nature, a lot of those minimal coupling that I will introduce indeed is realized in nature. If that was your question, by real, or if you meant real versus complex.
No.
Okay.
I mean, can we prove that if we find that the minimal representation, the theory, then can we prove that it is really minimal?
Good. So, okay, we can go back to that question again after I showed my discussion. Okay, but what I can say is that given a vector representation that describes a massless photon, then if I assume either charged scalar or charged fermion, then there is a machinery, which I will discuss, that get you that you must have at least this much term. You can add again extra term if you like, which is not random, you still have to be careful. But at the very least, you must have this much a term. In that sense, it's minimal. I see. So once it's specified representations, and then you ask how to couple those two sectors, I'm saying there is at least minimal amount of terms you have to add in a particular combination to be consistent. Thank you. Yes.
What is the difference between classical and quantum source?
Good. So by classical source here, I mean, I'm not actually looking into some quantum fluctuations, excitations, and microscopic interactions that happen inside of this blob. But I'm just like, okay, I don't know what happened inside of that. Somehow there's some machine. Okay, if you click the button of on your flashlight, it will shoot out the photon. So there's this classical source. Okay, obviously, if you actually look into that, there's a chip, there's actually QED is happening, there's something happens and the photon is created, and then there's colliminating and the shooting up. But I'm saying I'm totally agnostic, and I'm just treating as a source field in a sense that I'm not viewing this as a quantum fluctuating field, but I'm just viewing this as some function, classical function, somehow specified by hand.
Does it mean it is non-dynamical?
Yes, it is not a dynamical for now, but we will turn this into dynamical stuff soon. Okay. Okay. So that's the sense it's a classical source. Now, immediately you can learn something interesting and useful in the sense that, so let's now derive equations of motion quickly. So if you do it now, you should find that the equations of motion is this. Okay. So you can study many things. So first of all, if I now this equation and I just contract with the one derivative of with respect to nil, then left-hand side, obviously, this is antisymmetric, this is symmetric, it vanishes, right? So vanishes. Then right-hand side, I get this. So what this means is that massless photon can couple to only a conserved current. So I just call this vector-valued source to be current for now. So let me just call that right there explicitly. So if I call this, then this just tells me that even without doing anything about this, this can only couple to the conserved current. So this is the one left you can extract. Second, you should derive now Maxwell's theory from this. So Maxwell's equations. So it is instructive that you actually do it. Okay, using the fact that first of all, here's the classical source, which is 4 vectors. So let me have charge density and then actual current, right? And then we talked about this, and then this is related to the electric field and FHI, and this is related to the magnetic field. So using this, if you just actually work it out, you should get the set of Maxwell's equation. Not complete set. Okay, so anyway, so my focus is still thinking about this. So now, how do we actually run the machinery for deriving a minimum coupling? This is the lesson. No matter what that is, looks like it should come from a conserved current. And then if you ask yourself, oh, how do I get the conserved current? How can you get a conserved current? So we know that how to get, conserved current. You already know. You get it if there exists exactly. So that if you have a global symmetry. So here more precisely, if you had continuous global symmetry. So in this case, this conserved current is nothing but Noether's theorem, Noether's current, right? That's the contact point. So this is observations so far, and then we're gonna push this on in a sense. So what we're gonna do is the following. So here is a sector of a photon. So here we have a f mu nu, and here, for consistency reasons, we talked about this gauge redundancy, gauge invariance of a space-time dependent parameter alpha of x. And then we're going to take a sector, another sector, which is now matter sector, okay, which can be either fermion or scalar or something else, doesn't matter. So then I will write down a theory, okay? So I will write down a theory, Lagrangian, that has a symmetry, so U1 global symmetry. Which means that this sector now will give me a conserved current, right? So this sector will give me a U1 conserved current. So once I have that set up, then I will ask, okay, now I want to actually couple these two sectors. What that means is that here I started out with a global symmetry, which means that I will have a space-time independent constant parameter, symmetry transformation parameter. Okay, as you'll see soon. But here, obviously, it should turn somehow into space-time dependent parameter. So then the question is, so this is basically asking, when can we gauge global consistent? Okay, so we start with the global U1, and then we ask how we can turn that into a gauge or local version of invariance. Sometimes we will just abuse the language to say that gauge symmetry, even though I emphasized last time that it's never a symmetry, but it is actually just a redundancy of description. Okay, so that's the game plan. Let's run the machinery. And probably for obvious reason, that machinery is called a noise mount. This is how we will derive the medium coefficient. Okay. So in the first example, let's talk about the charge. At the charge matter, we talk about fermion first. Okay. So then, in addition to the photon Lagrangian, we're going to have extra Lagrangian. As we talked about, I will just have massive Dirac fermion. Okay. So then this thing has a global U1 transformation. So here I'm taking the single fermion. So I have e to the minus I e alpha psi, and then bar will transform oppositely. So here alpha, which is constant, is the symmetry parameter. This is U1 symmetry transformation parameter. And as you'll see soon, E will turn into a, if you want, so E later will turn into gauge function. But for now, you can just take it as a subparameter. And also, just as a comment, when I write this way, I'm assuming that the psi under the U1 transformation always goes with alpha times 1. which means that here assume that charge, this guy has a, charge 1. Charge 2 equal to 1 under that whatever you want transformation. And then likewise, psi bar, now we'll have charge -1. All I'm saying here is that instead of this particular form of transformation, you can repeat the same exercise with putting arbitrary Q, arbitrary charge to fermion, and that entire derivation will go through exactly the same way. But just to save some notations, I'm not gonna write that explicitly the charge. Okay, so here I'm assuming charge 1 fermion. Okay, so fermion case actually it's simpler than scalar, so let's actually do it. Sorry? Oh no, good. Thanks. Good. Was that why I saw many unhappy faces so far? Like I was like everybody is like so happy about the expression. Anyway, good. Thanks. Yes, that's sidebar. Okay, let's continue. Let's see how Noether's method works. So one way to think about Noether's current here is the following. Suppose I have a quantum field theory of action with some arbitrary field. So for just to denote arbitrary field, let me just use the psi for A. Okay, A denote possible multiple field against a phi, not necessarily for scalar. I'm just using it as general field. Okay. Then if there is a symmetry, if there is a symmetry transformation psi A, and then there's some shift, I know that it should be same as this. So that's what it means to be a symmetry of the theory. Okay. So now, so I'm gonna rewrite this as symmetry transformation parameter alpha times how this field is self-transformed. So this is always, transformed according to some alpha. So here I'm just looking at infinitesimal. So I'm just looking at the linear in alpha. Okay. Now, on the other hand, under a local version of symmetry transformation. So for instance, if I had a transformation that goes like either I alpha of phi of A, I'm saying instead of now I'm doing phi of A actually goes to either the minus alpha of x of phi A. So under the local version of the symmetry transformation, what would happen? So the variation of action now will be generically derivative of parameter alpha times some quantity. Okay, some quantity I call just Ju because this is a Lorentz vector. Whatever that multiplies, it should be Lorentz vector. So I'm just writing as Ju. And you see clearly that obviously, if you take this to be constant of space and time, as you would do for global symmetry transformation, you go back to the result that delta S is actually 0, so you find the symmetry. And then so here basically I'm just writing linear in alpha, but arbitrary derivative in this transformation parameter. Then whenever I had extra derivative, I dump everything here by doing integration by part. So this is only expansion in linear in alpha, but arbitrary order in the derivative. And in fact, this is how you can actually quickly derive in Noether's current. And another way of looking at this equation is that this is exactly capturing, so this particular form is exactly capturing obstruction to gauging the symmetry, lower symmetry. Right? Because if you just made the arbitrary local version of that, this is not invariant. And this is exactly capturing how it is not invariant. Okay, good. So with that, now we can work out for Fermion case. Any questions? Okay, so then let's work out this case. How things work. So let's first vary that Lagrangian. So let me call this particular Lagrangian to be actually just L0, because this is like zeroth version of the Lagrangian, and then we will start adding something on top of that. So we're going to have L1, L2, and so on and so forth. So if I vary Lagrangian L0, and in fact, let's just take a look at this. And then I'm going to do, actually more precisely, I'm going to do local version of variation according to this prescription. So what did you get? The only derivative part is when I vary psi going to this, right? The only derivative alpha you get is that you act derivative acting on the alpha here. Okay? So what do you get? So you get minus I cancels this I, so I get E times derivative of alpha of x, and then psi bar sits there, and then this has e to the plus I something, and this has e to the minus I something, so they just cancel each other. So basically I'll get gamma mu psi, because this thing has gamma mu, right? And if you look at this, this is exactly the form that this I will identify as a current. But once again, I will give a subscript 0 to say that this is a current based on the variation of the 0th order of Lagrange. Okay? So far, so good. And once again, this is exactly capturing the obstruction to gauging. Okay, now, so that's the step number 1. Okay, so that's the step number 1. Good. As a step number 2, what do we do? I want to gauge it, which means that once I do successfully gauge it, the final action or Lagrangian must be invariant, right? So eventually I want to design a Lagrangian such that under the variation of a local version is actually 0, right? That's what my goal. How do I do that? Well, then I should think about how do I cancel this variation. And so as a next step, we're gonna have a Lagrangian, which is in addition to the original one, I'm going to add an extra term. And that extra term I designed exactly so that I cancel this. So let's look at this. So if I vary this, and I'm just assuming delta of A for now, which it is the case, this. Okay, so this is how vector field transform under local version of transformation. And naively, if you look at this, with the minus sign correctly here, this variation will cancel that variation, right? E derivative of alpha plus E derivative of alpha times J0, which is minus E times derivative of alpha times J0. It will cancel that out. Obviously, let's actually check it out. So under the local version of the variation, L1, it should go like local version of variation of L0 minus E variation of A J mu, and in principle, which is crucial, minus E A mu variation of J0, right? Under the local version of transformation. So that is the full variation. Now, nice thing about the fermion is that this is 0. In other words, 0th order current is gauge invariant. And the reason is because this current right here for fermion is actually only polynomial infinite. Meaning, basically I'm saying there is no any derivatives in the current. Okay? So for fermion current, it is actually again non-derivative. And so this term is nicely canceling. And in fact, as it is designed, therefore, already this first iteration is enough to satisfy this property. So we arrive at the point that once I actually take this as my action, in fact, this Lagrangian is actually gauge invariant. So let's actually write out fully what this looks like. Okay, so now I'm going to write out full Lagrangian. L1 which had a photon field, although I just dropped it, just for to save the space. Then sidebar, this, and then E A mu Z mu 0. So let me rewrite this part again. So I have sidebar, this, and this is minus E. And remember, this had gamma mu here. So since photon field commute with either all of the fermi period, let me just move in. I can rewrite this as sidebar A slash psi, and then there's a mass term. Okay, so if you look at this, that look very similar. You might be tempting, even if you're not. From now, you're a tempting person to combine these together. So that looks like this. The minus sign, there's one I E. This psi minus psi bar m, m psi bar psi. So now I can call this big guy, which is some modified version of a derivative. So I'm just gonna call that to be a D slash, capital D slash, which is nothing but this. And the name of this thing is called what is called covariant derivative, which I will also provide you another explanation soon. So overall, then my theory looks like photon term, as we had, plus psi bar, and then almost same as before, except little partial derivative replaced with the covariant derivative, like so. So this theory is now fully gauge invariant, U1 gauge invariant. Yes.
이번 과정에서 J0 우리가 지금 펄미널 필드에 대해 생각하고 있는 거잖아요. 근데 저 J0 우리가 저 벡터 필드의 J랑 같아야 될 이유가 뭐죠?
So your question is, I just vary the first action, meaning the literal it is with respect to local version of the transformation, and this is what is found, and this is the noise form. And you're asking why this should be the same as something else. You mean this?
No, 근데 왜
You mean here? So this is a general explanation, right? So when I talked about this, for any theory, if there is a continuous symmetry, this is how you can find Noether's current. I'm saying this is here in this case, this is Noether's current.
Oh, no problem. Okay.
Okay, very good. Any other question so far? Yes.
Is it a coincidence that Noether's current comes from this derivation of KG?
You mean this?
Yeah.
No, it's not a coincidence. This is, this is supposed to work that way. Because so this is if you wish, there's a separate derivation, right? So it's by varying action, there's the equations of motion part, there's a surface term, and then since Lagrange can shift by total derivative, you can derive that way. That is how you learn Noether's theorem, but this is equivalent in a sense and is guaranteed to give you the same Noether's current by the logic that I explained, because action by construction should be invariant if this is constant. Therefore, if I turn on auxiliary x dependence in it, we know that if this is still has a notion of infinitesimal transformation, then linear in alpha should always take this. So this is generic. It's not a coincidence. Another question? Yes.
Is there any no coupling in this Lagrange yet? Right?
Here in this Lagrangian,
No coupling.
no coupling.
Between the vector field and the
There is. And remember, this covariant derivative indeed include a coupling between the photon field and the fermion field. In fact, that was exactly that term. I just rewrote. I just combined this with a partial derivative to rewrite in terms of this new notation that is called a covariant derivative.
So, in the Fermion Lagrange, we have global mode.
Yes.
Why do we it is something artificial to introduce the local rule.
Good. So that was the motivation part. Let me repeat it again. So there's a photon part which had a invariance, even though it's not a symmetry, invariance under local version of U1 transformation. But the photon had a specific way to transform, meaning it's shifted by derivative of alpha. Now, if I want to couple some matter field to the photon, I say that the only, at the minimal level, the only way photon can couple some matter field. Now you know that I start out by saying there's a classical source, but now you see how that classical source exactly look like, which look like this. So in fact, now I can draw a diagram. So previously I said there's a source which is shooting out the photon field. Now you know exactly what's happening inside this block. It's nothing but there's a fermion and an anti-fermion fuse actually to produce A. Okay, because psi warp psi coupled to A mu. Okay, and this vertex is also nothing but minus E times gamma mu. So we even know the final rules exactly. So now, again, your question was why we have to gauge, why we have to talk about the local version of that. I said, whatever the coupling is, this should be conserved current. But it cannot be coincidence. Conserved current is not a random concept. It only comes from if you wish there was a light at some point that it had a global symmetry. So taking that as a motivation, I started out with a theory that has manifestly global symmetry. But then here I'm showing that in order to couple consistently, so in other words, if you just, this is not gauging here if this does not transform at all. Sorry, let me say that again. Now I believe this is not invariant under the gauge transformation because it shifts. Although it also shows that this should be conserved current. Okay. So basically, what I have demonstrated here is that starting from a theory with a global version of symmetry, then that sector can couple to this photon sector only if I can promote that global version of transformation into a local version of transformation. And the consistency demand that there's no random form of interaction, but it should be exactly this one. So that's what I demonstrated. And I will demonstrate also for scalar case, which is slightly less trivial. You will see actual power of this machinery. Although, in other words, we will have to do another iteration there. Yes.
Because every laser current can be coupled to photon field like this. In other words, we can convert every global symmetry to the gauge symmetry.
No, the answer is no. The answer is no. And this particular symmetry here I wrote down has another name. It's called the vector-like symmetry. What that means is that if you have a global symmetry, you can check some fancy stuff called anomaly. So more precisely, if the global symmetry doesn't have any anomaly, either with the gauge symmetry or with it on its own, meaning there's a fluke anomaly, then you can promote. So accidentally, I start out with a theory that has a vector-like symmetry that does not have any of the anomaly. That's why I succeeded in actually gauging. But since here we're talking about only perturbation theory, so far we haven't talked about any anomaly. Yeah, but that's the answer to your question. Yes.
Can you explain one more time about the field A mu?
Yes.
How the field A mu is related with the vector field F? Can you explain one more time?
Vector field
A.
F.
F.
F mu nu, you mean?
Yes.
Okay, so yeah, so F mu nu, we already did that, right? So here F mu nu.
Yes. Yes. So my question is in the step 2,
Yes.
why the A
Yes.
have to be consistent with the definition of this F?
Yes. Good. So your question is why that guy is actually this guy.
Yes.
Okay. So because that's what I wanted to do. In other words, what I mean by that was that I started with a sector of photons. And then I have another sector of matter field, which has a global U1 symmetry. And what I wanted to do is that I have a quantum field here, A mu, and then I had a quantum field of psi bar. I wanted to couple these two sectors. Minimal coupling, okay, in a minimal sense. So so therefore I don't want to introduce another A field, but I want to use the A field that I started with, and then I wanted to couple that to the matter field.
So, but in your explanation, the definition of A is come from the gauge transformation alpha. So
Yes.
it's also related with the definition of F in the vector field.
Yeah, so obviously I started out with this sector and I knew that there's A field which transforms like this. So basically I am identifying gauge transformation parameter alpha with a global symmetric transformation alpha. In that sense, so I had a local alpha x, the global alpha. I'm turning this into a local version of that. So I said that I'm gauging that global symmetry and turn that into gauge invariance. Yes.
So we gauge the Yuan symmetry, so that saying you cannot be letter current for that Yuan symmetry.
Good.
Am I right?
Yes.
Then-
So yes.
Is there some global symmetry that having JNU as each electron?
Very good. So that's a subtle question actually, and some people can say when you take a gauge U1, which means that you are allowed to do a arbitrary local transformation with arbitrary alpha x, and one choice of alpha x is constant alpha. So if you have gauge U1, looks like you also have a global part of it. And this is related to the asymptotic symmetry. So if you send the photon to the infinity of the boundary, eventually there's some leftover symmetry called asymptotic symmetry. This can be viewed as a current associated with that symmetry. So that's answer number one. Answer number two, not that I'm totally on top of everything. Answer number two, you might say, oh, there was a zero form symmetry. Okay. Am I supposed to? Okay, accidentally I said.
Is it for one form symmetry? Okay.
Yes, so good. So that's what I was going to say. Since you know the concept, let me just say it. So naively, this you say this has like charge and current, right? Right. Now, you might say, okay, then if I look at the divergence of E, I can measure charge and so on and so forth. The right answer is that there is secretly a symmetry. And that symmetry is called the electric one-form symmetry, and there's a magnetic one-form too. So now, actually, what's exactly happening is you have an electric one-form symmetry whose conservative current is supposed to be this, which is broken by the existence of this current. And then what you're actually measuring is that at each fixed time, there's a charge. And then you can embrace that with two surfaces, because I'm looking at each time slice, the surface, and then you keep track of the entire word line that is actually measuring this wall from the electricity. That is the modern version of the answer to your question. Okay, good. So, but hopefully you understand the prescription, okay? Because I'm gonna do slightly more complicated now, okay? Starting with Glover, let's try to gauge it. I fail. Let's try to rectify it. I might succeed already. I'm gonna do scalar. If you do it, you're not gonna succeed. And we will have to do one more step. Okay, so let's do that. Let's start. By the way, keep in mind this expression, okay, covariant derivative. So replacing partial derivative into a covariant derivative, trying to remember at least the naive form of it, okay, there's a partial derivative and the gauge field, which I will, again, give you another explanation. Okay, so now what I'm going to do is that I'm going to take a sector of photon and then I'm going to take another sector, which has a scalar. So I'm going to take a sector of complex scale, and it can have a mass. Do I care? Probably not. Probably you. But for the discussion, this thing is not important. Okay, so I'm just gonna drop it. But you can add. There's nothing changes. So this thing again has a U1 transformation Glover symmetry, which you can take to be alpha phi. Dagger having an opposite charge. So far Glover transformation. So this is Glover U1. Now I will try to gauge it. Okay, so let's do it. Okay, so now let's make as a step number 1. Let's make a local version of the transformation. Okay, let's do it. So again, I want to read off the term that is proportional to this guy. So let's see. The first, from this term, I have a I, E, so E, and then there's I, and then derivative of alpha, and then phi. So there's a phi, but I haven't touched this guy, so there's this, okay, so that's the first contribution, by varying only this guy, not this guy. The second time, I'm leaving this guy alone, so I will have a derivative of phi dagger, and then this will give me minus IE derivative alpha. So I have E derivative alpha, so I have minus I have minus phi. Okay, so that's up to plus minus sign, blah, blah, blah. I think this is exactly the answer. So just like before, you see that this can be identified as my zeroth order answer from my current, Noether current. Okay? In fact, last semester you actually looked at this and you derived this and studied that and so on in a different perspective. And again, this is absorption litigation. So let's go to the second step. So naive trial to cancel this variation is that, okay, let me promote non-Lagrangian, including the first term, and this has a plus E derivative of alpha current. So naively, if I write it as gauge field this, that looks like a good trial, right? However, note that here there is a key difference between this and that Fermion case. Here, current, zeroth order current is not gauge invariant. And key difference is because now, as you see here, the zeroth order current is a derivative, has a derivative in it. Okay? Previously it was totally polynomial, so it was gauge invariant. Now it has derivative. This will have immediate consequence, so let's study that. So if I vary this, obviously there's that. And then the second term varies as derivative of alpha, this. So that's by varying the A mu first. And then I will have. So the fact is that obviously this variation exactly canceled this, which was nice. And in the Fermion case, since this was 0, that was done, right? So we achieved the ready job. But now this is not 0, so let's actually work that out. The variation of the current, which is this, is the following. Okay, again, I just need to read off the derivative term, because if you were not, it was gauge invariant. So this has a minus I, so it cancels this I, and then I get E derivative alpha, and then phi dagger phi, which I write it as a phi squared. And then second term, there's a minus sign, there's I, but this has plus I, so minus plus I that again makes up 1, so it actually adds up. This is answer. Now, you see that now, at the second iteration level, what multiplies the derivative alpha is now actually polynomial in field. So now this is actually gauge invariant. So we anticipate that in the next iteration, we're going to succeed. Okay, so let's now move on to the third iteration. So now we're going to design L2 as L0 minus E A mu J0, as we have already. Now I want to design extra terms so that whose variation cancels this. It cancels that variation term, right? How do I do that? So this has a minus E squared. So I want to have E squared. And then the variation has one factor of the derivative alpha times A. That looks like I get it if I had A squared, like so. And then there's factors of 2. So since this is A squared, I get factors of 2. And then since this is polynomial, I have this multiply. Okay? So you should convince yourself now, hopefully it's already clear that now this is gating there. Because it's square 2 times A times variation, which is alpha of x, sorry, the derivative alpha, and then 5 squared. So that exactly cancels that variation. And done. Okay? And this is gating very quickly. Otherwise, we will have another iteration. Okay? So I arrived at the point now so that I can write down what is the final theory. So let me just write here. So it had a photon field, a photon sector, and then this had a naive kinetic term for the scalar with, yes.
I'm a little bit confused. I think L2 should be equal to L1 minus blah blah times.
This is L1.
L1.
So this is L1. Sorry, say it again.
That is L1.
Yes, that was L1. So on top of L1, I just added extra term so that it cancels out the variation of L1 itself, which is this.
I see.
Good? Good.
Thank you.
Okay. So good. So then the final result we get is that so there's a zero floater kinetic term for the complex scalar, which is partial derivative, and then this thing had a phi dagger derivative phi and Hermitian conjugate. And now there's extra phi squared. So here's the claim. If you, at the end of the day, you should get plus IE A mu acting on phi dagger. You should be able to combine everything. Minus IE phi. So everything should be able to combine this way. So obviously this has a zero floater kinetic term, and then the linear term you should get from taking one photon from that side and then just partial derivative. So that's like A phi dagger derivative phi. So that's one of this term, that term. And then the other combination should give you Hermitian conjugate. And then finally, this term is obviously if you just look at a term, that is a E squared phi dagger phi system. Okay. So once again, we arrive at the point where it looks like consistent gauging is same as replacing partial derivative into a covariant derivative, which has the exact same form. Oh, sorry. In case you were a little bit confused, I meant this sign. Okay, so just like Fermion case, this is a recipe. Yes.
What about derivatives in field strengths?
Derivatives at which field strength again? This?
Yes, F mu term.
So this is still the same.
Even if we change
This was gauge invariant to begin with.
by construction, okay.
Right. So nothing to be fixed, but I just turned scalar sector into gauge invariant.
What about partial alpha phi squared?
Partial alpha phi squared. Oh, you mean the second order in alpha?
Yeah.
Okay, and you can check that this is gauge invariant for arbitrary finite transformation. But here I've demonstrated just using an infinitesimal version of that. But the answer is that this is true for arbitrary finite gauge transformation, which I will show now. By the way. Yes. Another question. So I introduced a covariant derivative this way because this is, if you wish, a physical way of thinking about it. Okay, starting with the global and the gauge it and then turn that into a covariant derivative. Now, let me give you an alternative explanation to this covariant derivative. Okay, and showing that this is true for finite version of gauge transformation. Any question?
If we add the mass count, then the Lagrangian will change by mass.
No, so if you look at this, right, this is a polynomial, and then if you make a local version of transformation, this is already in there. So nothing to be fixed. So you just still have that term there. It is only the derivative that causing the trouble because it pulling down a derivative alpha. Okay, any polynomial will stay the same. All right, good. And in fact, so this is the version of the Noether's method for U1, right? So you either you just have to do one iteration or two iterations. It's done. So for non-abelian gauge theory, like SUN, you can still do it. You may have to do a couple more iterations. And people actually did this for supergravity. Okay, so there's diffeomorphism, they did it. And if you do it, there's like pages of pages long iterations. Eventually they can do it. I have not done it, and I don't think I want to do it, but it's possible. And another example, I'm not sure if that makes sense to you at all. Whoever took my advanced part of this class made sense, hopefully. There's something called the Weisman-Witten term. But anyway, and then people try to turn that into gauged version of that. And then the person who I think achieved the first time was Ed Witten. And if you actually read his paper called The Global Aspect of the Symmetry or Global Aspect of Current Algebra, there's a literal page-long expression. And he literally ran this machinery to get the gauged version of that. Okay, so sometimes people actually work it. Okay, good. So now I want to give you an alternative viewpoint on the covariant derivative. So either for Fermion or scalar, which had the same form. So we had this. So let me just demonstrate with the scalar. Again, it's the same for a Fermion. So the minimal prescription. Hopefully you see why I called it a minimal, because this is the minimal amount of structure you have to have in order to be at least consistent with the gauge invariance. Okay. So that was turning this into a covariant derivative. And then it had a form that there's a partial derivative, E field, gauge field times phi. Okay, so here is an alternative way of deriving this formula or seeing this formula. So why it's called the covariant derivative. So the motivation is the following. Recall this guy goes to like E alpha phi, right? And then once you have this linear transformation, it's so easy to construct an invariant. Even for the local version invariant, obviously, if you just write down phi dagger phi, you know it is invariant, even if it is a local parameter, right? Because they just cancel. So if, which is now, if this were transforming as nicely homogeneously like so, right? Then again, it recalls. So I just do it. If I wrote this, I knew it is invariant under the local version. But the trouble obviously is that this is not true. So that therefore, naive partial derivative of field does not transform covariantly under the local version of the transformation. Hence, it is less clear how to construct the invariant, right? So the whole point is that can we turn this into something? I don't know. Let me just call it for now this, which without knowing anything about it, such that now this transforms as nicely as possible, right? Covariantly. Okay. So if that was the case, obviously it's immediately clear how to construct invariant. That's the motivation. So now let's actually work it out, how we can construct that, which is not that difficult.
Oh, before you get into that part,
Yes.
does the fact that the nether current is not gauge invariant have any physical implications?
Good. So, yes. Immediate physical implication is that you are not allowed to ask any question about asking correlation functions of gauge non-invariant operators. There's no physical observable associated with that object. On the other hand, we know that for fermion case, obviously we ask a lot of those questions. And that's because it is a gauge invariant. So therefore, this is not an operator in the set of observable operators. So that's immediate physical consequences, if you want.
Then it is related to we do not consider the anomaly from scalar fields.
Okay, good. Is that how I interpret? I mean, that is true statement, meaning the scalar doesn't come in 4 dimensions. I mean,
Yeah.
4 dimensions scalar doesn't come with a anomaly, chiral anomaly, although you can have a scale anomaly. I'm not sure if that is directly related to that. Because in principle, I can imagine, so you see, on the other hand, I can construct another current out of the scalar, which you will see that immediately gauge invariant. So if obviously, as I was about to do it, if covariant derivative actually transform linearly and nicely, then this is gauge invariant. And I wonder, actually, you can, I think if you actually vary with respect to, because if you naively vary with respect to local version, this is gauge invariant, so you're not going to get anything like this. But this is gauge invariant. In principle, there can be a observable associated with this. So this may be counting the number of scalar particles. But I don't have off the top of my head, I don't see any immediate connection between this and then, absence of anomaly. But that's a good question. Okay, any other question before now I'm going to just construct the covariant derivative from this perspective. Okay, let's do it. So derivation is now pretty clear because how do I set up? Well, this is a Lorentz factor. Right? So this is Lorentz factor. So this should be related to obviously partial derivative because that's how I started. And then I want to modify in linear sense. So I'm going to put some number c, which I don't know yet, times this, because this is minimal modification I can do. This is Lorentz factor, this is Lorentz factor, at least it has the correct structure. Okay, and then I'm going to demand that that object transform nicely as this. Okay, so that's how we want to do. So let's do it. So this transforms under, well, phi goes to e to the minus p alpha phi. You see, there was a question that I'm actually looking at not a infinitesimal transformation, but I'm just taking a finite transformation. So good. Let's look at the first. So first, when the derivative hit the field, not the alpha, obviously I will have minus e alpha, and then acting on this. Okay, so by chain rule, and then this term also has a transformation that behaves like e alpha c. So this is from the variation of that thing. Okay, so that's the first term. And then the third thesis that I'm missing still is now derivative acting here. So that will give me minus I e derivative of alpha. And then I still have minus e alpha phi. And then I have to take into account how A transform, which I know. Derivative of alpha, and then A mu. And then this has its own transformation, e alpha. Okay. So I literally plugged in and computed, and that has these two terms. And then if I plug in here, I have that term. That's all I'm saying. Is that clear? Or am I missing something? So let's see. If I plug in here, this term should be for this, right? Variation of that term. Then if I look at this, so I'm just gonna instead A plus this minus E of 5. So this will give me two terms. One is that, second is that. Right? So I'm taking now not an infinitesimal but exact.
선생님 그 마지막에 A가 지워져야 되잖아.
Oh, I'm sorry. Yes, you're right. Thanks. Yes. So you see now that if you combine the first two, well, the first two in this way, this nicely combined into derivative plus CA y. So that was the covariant derivative. So this is what I wanted to have. That means that I want to cancel out these two terms, right? To have a homogeneous transformation property, because I then wanted to get. And that's clear because that times that, as this cancel that, which means that I need to take C, it's a plus, I'll cancel that out. Okay. Then you get covariant derivative by construction as this, which transform homogeneously under the local transformation. Okay, so that's about minimum coupling and covariant derivative. Now we will move on to propagator. Questions? Okay, good. So now, by now, at least you know how to write down QED action. So you know photon, you know fermion, say electron, you know how to couple photon to fermion, right? Write down covariant derivative. That's the QED action. Okay, so once we talked about how final rules of that thing, you can start computing, Coulomb interaction, complex scattering, Thomson scattering, all of that. Okay, we will have one class on that of this. Yes. 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 So remember, the motivation to construct this, hence fixing the C, was that this as a combination transform under the local U1 as this homogeneous transformation. Which means that, but this entire thing arbitrarily now, with arbitrary C for now, transform not only the first line, which is what we want, but also the second line. So we want to basically choose a C such that this thing is 0.
두 번째 줄에 맨 마지막 텀이 어디서 나온 거예요?
Okay, that comes from a variation of A head, which has A in the short by. Okay. Good. Okay. Now, next thing you want to talk about, because eventually you want to talk about QED and computing processes, you want to talk about photon property. And we will discuss this slightly different way from what we have done for scalar and Fermi. So, well, the way we have talked about the propagator is we want to first of all define a contraction, right? So far, but once again, I'm going to do it slightly differently. So contraction is obviously difference between time ordering and then normal ordering. So we can do it, but we're going to take slightly different path because it will also illustrate some other aspect of this sort of discussion. So and then obviously if I look at the vacuum expectation value, so that was basically what's defining a final propagator. That is the same as contraction, and contraction, remember, is commutator. Commutator is the C number. It's the same as taking vacuum expectation value. So we wanted to compute, basically, we want to compute time ordered correlation, 2-point correlation function of photon field. And so let's write this as a Fourier transform. There's a Fourier transform, E for P, e to the minus P, x minus y, and then momentum space propagator, which let me write as I times sigma mu nu. Okay, so far, this is a definition of dislocation. Okay. And just to remind you, in the case of a scalar, which will come back again and again, and today, hopefully, if there's a time, we'll see. Eventually, if you have done it, we get like Fourier transform, and then momentum space propagator in the form that I over p squared plus minus y squared and I XOR. So we will spend some time to think about talking about isomer prescription to understand the physical meaning of that. So anyway, so the goal is to derive this. Okay, so what is the photon propagator? And the way I want to discuss this following Maxwell's QFT discussion, which is nice, is as follows. So one way to think about that result is that if you have a scalar Lagrangian, then you can have it look like this: square minus m squared by square, and then you can do the integration by part to write it as minus phi box plus m squared phi, right? And then if you go to the momentum space, like we Fourier transform, then this will turn into phi p squared minus m squared phi. And then you notice that propagator is roughly speaking an inverse of this factor up to I epsilon prescription that we need to understand why we need that. Okay? So we're gonna basically follow this path. So let's actually look at this. So we start with the photon Lagrangian for photon. And then again, we're gonna couple to some source field. Conserved source field, as we talked about. Then equations of motion, as we have written a million times by now, is this, good. And this is a second order partial differential equation. And you know how to solve second order partial differential equation in the presence of source, right? Basically, you want to first get the Green's function. And once you have a Green's function, you can get the field by acting Green's function, not acting, like multiplying Green's function on the source field, right? So let me write that expression, what I mean by that. So let's first clean up this. And then using the definition, A nu. A nu. Okay, so far so good. So let me clean up this box. Okay, this is box. And then I want to flip the order. I mean, it doesn't matter. But I want to write it as G mu nu A mu. So that is manifest the correct expression. And then mu nu A mu. I just flipped over the location of the mu index is equal to J mu. Good. So now let's pass on to the momentum space. Let's do the Fourier transform. Okay. By which I mean you assume you think this is a finite solution sort of thing. Okay. So if you do it, then you get p squared from this G mu nu. And from here you get plus, because you have a 2 derivative, you get the extra minus sign, p mu, p nu. This is the equation. Good. That's the equations of motion. Okay. Now, Green's function is then defined as so given this differential operator, right? So if I write in a what is a good notation for differential operator? Is there a conventional notation? No. So that means I can do whatever I want. Good. So I'm not notation. Differential operator. Cool. Okay, acting on there is actually notation. So we have a fancy differential operator acting on this is J, right? This is our equation. Okay, and then Green's function is basically taking a differential operator, and then this is my notation for Green's function. This is delta function, right? This was this, right? So once I can determine my Green's function, so this is Green's function, then a photon field can be obtained. So a photon field can be obtained if I had a source by doing this, right? So by which I mean sometimes you have to do the integration, but I'm just taking a simplified notation. Okay, good. And if you look at the definition of the Green's function, it's clear that this Green's function is basically inverse of the differential operator, right? It's supernaturally matrix multiplication, and the product of 2 is 1. So this is inverse of that. Okay, cool. So let's just do it. And in fact, when I say that this is basically inverse of that, that's exactly what I meant. Now there's an issue. There's a problem for photon case. So what is the problem? Well, let's take the Green's function. So sorry, let's take the differential operator, but in the momentum space. This is our differential operator, and the problem is that if you just do this, so that is this is p squared p mu minus p squared p mu, so that's 0. So what it means is that this differential operator that we want to have has 0 eigenvalue. What it means is that determinant of this thing is 0. What that means is that as we wanted to have inverse of the differential operator, this is non-invertible. Well, that's correct word, but I really like this word by the way. This is non-invertible. Yeah, because for a second I thought I said something wrong. Just like that, I said like 0.05. For a second I was. This is non-invertible, which means that I can define this. I can determine this. It would be funny if this is the end of the lecture, but it's almost the end of the lecture. I could have just said, okay, it's not invertible and no this. And photon does propagate, and there's no QED. QED is all wrong. Let's continue. So now, once you face this problem, how would you, resolve this problem? In order to tackle this problem, you first want to understand the origin of the non-invertibility, right? Then you will have a chance to rectify it. So let's first, understand where this non-invertibility come from. So let's go back. So that's how we checked it. Now let's look at this equation. If this existed somehow, if Green's function existed for the massless photon, what that means is that for a given source field, A mu is uniquely determined, right? So if this is fixed, and if I give me fix the source, you get the fixed A mu. Right? So that's how things work. However, we have talked about all the time that, well, that's not true because A mu is defined modulo or up to this gauge redundancy. So A mu is never uniquely fixed unless this redundancy is lifted or killed. So that's the source for non-invertibility of this thing, because even if you give me a well-defined source distribution, right? You cannot get a unique A mu, which means that this cannot be a uniquely determined at this level, which means that obviously you should expect that this is non-invertible, meaning it cannot be inverted. All right, so then in order to get an invertible situation, what we have to do is that given source, I have to kill this redundancy somehow. I have to remove this redundancy. So then, for a given source, I will have a unique well-defined Green's function. I will get unique A mu, since I somehow remove this redundancy. So that business, therefore, we have to do it. So basically, we have to get, somehow remove this redundancy. So that process is called gauge fixing. So therefore, in order to actually define or fix or determine the Green's function and hence eventually photon propagator, we have to first do gauge fixing, okay, and then get the invertible differential operator. So that's the step. Let me see. Okay. Okay, so we have to discuss gauge fixing. But we need to detour a little bit. So we're going to detour a little bit first, discussing gauge fixing, and then come back to this question, and then do this. I'm debating 10 minutes will be enough. Okay, let's do it. I think we can do it. At least we can just talk about the gauge fixing, and then we can come back to this discussion next time, because I want to spend some time discussing this I-form distribution. So let's quickly study the gauge fixing of the photon, massless photon. Are there any questions before? So 10 minutes. I'll finish this. I am on 3 minutes. Okay, so let's do it. So let's talk about gauge fixing. And this also answers one of the questions that raised last time. Like for massless photon, why there are 2D field? And I don't think I answered fully during the lecture. I gave some pseudo answer, but this, at least for photon case, will give you a answer. So let's do the gauge fixing. Okay. So well, I have to write an equation of motion again, which I erased. Cool. So do I remember? Do you remember? Okay. Do I have to do it again? Oh no, I don't want to do it. Okay. So I know. Good. So I know that since there's this term and then done. Okay, good. So some time. So this is the equation of motion for photon. Okay, just the photon sensor. Now, in order to talk about the gauge fixing, let's actually write this split into the zero component and then spatial component. So zero component, it has, let's write 0 square A0. So I'm taking this guy to be 0, and then pi square A0. So that's from the box term. And then I have 0, but I'm free to lower it because metric is plus for the zeroth component. And then I have this guy. So there's 0, I0, if I look at the 0, 0 component. And then it will have a 0, I, 8i. Okay, so that's the zeroth component equation. Okay, good. So let's write down the equation for I component, spatial component. So that's plus of AI. There is a reason why I split that way. By the way, before I actually proceed with the I component, you immediately already see that this thing cancels that. So that's the equation. And here we have a I, or let me lower it, I. And then I have 0, 0. I, J, J equals 0. Cool. Okay, so here are two equations we are dealing with. So, what is the concept of gauge fixing? Suppose you want to figure out all possible, configuration of a mu x field. So we're going to look at all possible configurations and then the fluctuations and so on. But then if you somehow find one configuration, there is a million, not just million, actually, infinite amount of other configurations, which is basically equivalent. Right? So when you want to talk about a single configuration, you're actually carrying the infinite amount of configuration, which is at the end of the day basically the same thing. And that of course comes from the gauge redundancy. So you can remove that if you say somehow this is not allowed to do anymore. Or in the language of path integral, which we will introduce after this part of the discussion, hopefully in 2 weeks or something, when you solve all possible field configurations, in a sense of actually integrating over all possible field configurations, path integral of gauge theory secretly has infinite amount of integration because you had this, right? When you want to integrate over one thing, there's an infinitely related physical equivalent configurations you're actually integrating over. Okay, so if you're not able to come with something, you will get infinite all the time. And so you will basically cut and define, there's a basically unique configuration, removing all these redundancies. So that's the gauge fixing business, and let's actually demonstrate here. So first of all, AI, the spatial component, eventually this will include a physical propagating degree of freedom, will transform under the gauge transformation as this. So which means that for arbitrary function AI, I can already choose alpha parameter such that the transformed version, so let me call that to be, oh, sorry. Okay, oh, this is true. But then just so that things become a little clear, let's write this. So what it means is that for any choice of AI, well, this transforms like that. And then what I can say is that I'm going to choose alpha freedom. So this is my freedom. Now I'm about to give up on my freedom by saying that, no, I'm not going to take arbitrary alpha. Instead, I'm only allowing alpha that satisfies, if I write this as transformed a divergence equal to 0. So this equation is a condition of alpha. So you started out with arbitrary alpha. When you impose this, obviously, you reduce the space of alpha down to all the way down to something that only satisfies this condition. Is that clear? So this condition is called Coulomb gauge or gauge fixing. That whenever you go to the a basis where this is always true, which means that now you're not allowed to take any arbitrary alpha, but only the alpha that satisfies this condition. Okay, so the space of alpha reduced significantly. Okay, so now we are in that Coulomb gauge. So then in Coulomb gauge, so the equation of motion simplifies significantly. Let's see, because this is 0, that is 0. So basically, we have this observed component, and then this for the spatial component. And one thing that you want to keep in mind is that this is now, there's no time derivative, right? So this is not quite evolution equation actually. Okay, and there's a reason behind that. Now, let's actually check whether we completely fixed alpha or there is still a little bit of a freedom left over, even after imposing this condition. Okay, so now what we have to satisfy is that So for alpha such that equal to 0, it is still allowed. Is that clear? So suppose I fix the gauge into the Coulomb gauge, but any function of a function alpha that still this is 0, then starting from the Coulomb gauge fixing condition, this is untransformed, right? Because under that I get this shift, but that is 0 by definition. So example of that, obviously, for instance, if alpha is only a function of t, obviously this is trivially satisfied, for instance. But I don't need to take only a particular function, but I'm still considering arbitrary function of x and t so long as this solves this equation. Okay, so this leftover freedom is called a residual gauge invariance or gauge redundancy. Okay, now we can use that gauge freedom actually to get rid of A0. So let's see how that works. Okay, so by the way, at this point, let me already pointed out this. So we started out with an ungauged fixed version. We fixed it once, and then in that fixed version, this has to be satisfied, right? So oh, by the way, good. So I'm going to make an important statement here, but before that, let me say one thing. Remember, in photon case, Maxwell's case, this is not automatic. What do I mean by that? Remember, in the massive case, because part of the equation of motion had m squared a nu, if we take another partial derivative using the antisymmetric version of that thing, you got this equation, right? So this is how you only project it onto the transverse part. But in the massless case, obviously this term is 0. So this transversality condition is not automatically satisfied as yet. So when we study the equations of motion or photon theory, we are still talking about 4 degrees of freedom. And then we gauge fixed once, and this will reduce 4 AMU degree of freedom down to 3 degrees of freedom at this level. Now, let's come back here. So I said, okay, there's a residual gauge transformation, and then A0 transforms is obviously 0 alpha. Okay? But then this alpha always has to satisfy this equation, because I'm already in the Coulomb gauge. So now I'm not allowed to take any alpha, but only the alpha that satisfies this equation is talked about. But this is exactly the equation that A0 itself satisfies. Right? So this is the same equation as that. What does that mean? What that means is the following. So in Coulomb gauge, so under the residual gauge transformation, then equations of motion for A0 goes to this. And then, A0 alpha, right? So this is how equations of motion changes under the residual gauge transformation. But the crucial point, as in hopefully you see immediately, is that this still remains to be 0. So we are still in the Coulomb gauge because this is 0, that was 0. So I'm still in the gauge where that is satisfied. So this is just reconfirming that indeed, whenever I do make extra transformation that satisfies this function, I'm still remaining in the Coulomb gauge. Okay? This is just reconfirmation of that statement. So good, but then this allows me to eliminate. Therefore, I can use this residual transformation to eliminate A0 completely. Meaning I can now go to the extra gauge in which A0 is actually 0. I can just go to the basis where this is actually 0. Not basis, but I can fix alpha. If I do that now, I completely lose the freedom to use any alpha anymore. Okay, so now I don't have any more freedom left. So combining these two, so I reduce degree of freedom by 1 by doing so, then using the Regina transformation, I can also eliminate another. So eventually now I go to only 2 degrees of freedom left. And this is one way to understand why photon has 2 degrees of freedom, rather than 3 or 4. Okay, so I stop here, but next time, so this is, if you like, discussion of the gauge fixing. Next time, I will come back to this question of photon propagator, since you now understand what it means to be fixing a gauge, we will derive pi medium. Okay, so that's all for today.
우리 다음 주에 수업이나?
Yes. So when was that? Sorry, let me just turn this off and then we can talk about that.